Okay, good afternoon, everyone. Today I am here to present my paper titled A Flexible Wearable Microstrip Antenna for Healthcare Application Using Foam in the ISM Band. My name is Kailash. I registered as MICRT STEM 23041 number under the supervision of Dr. Vaibhav S. Hindre sir. This is the outline of my presentation: introduction, literature survey, geometry, selection, design, result discussion, conclusion, and references. Basically, wearable antennas are those which can be owned by a person and have the capability to connect with each other directly or through embedded cellular connectivity. Wearable antennas are used within the context of wireless body area network. In a wireless body area network, the antenna is the key component that supports wireless communication, which includes in-body, on-body, and off-body communication. Basically, W-band connects sensors, actuators, and IoT nodes on a human body that also connects over the clothes or under the skin, establishing a wireless communication channel. Wearable antennas can be employed on people of all ages, athletes, and patients for continuous monitoring of vital signs, oxygen level, and stress level, among others also. This is the basic application diagram that will show where we can use wearable antennas for measurement of body parameters. Few of them are temperature sensors, glucose sensor, sweat sensor, EEG, ECG, or SpO2 level also. These parameters can be scanned and can be forwarded with the help of wearable antenna to the doctor or the user level. Along with this, uh, we have some challenges in designing of wearable antenna. The first and very important, proximity to the human body. Basically, human body is a lossy material for electromagnetic waves. That means whenever electromagnetic waves comes into the picture of human body, it is completely absorbed. Or we can say there is a conversion of these waves in terms of heat. So this is one of the important challenge while designing the wearable antenna. Second is very limited volumes. The size should be very small as possible compared to the other antennas. Then SAR value estimation. Whenever it comes to the wearable antenna, estimating a SAR is very important. It should be less than 2 watt per kg. Then apart from this, few challenges like bending, stretching, and coupling. Overcoming these challenges, I have gone through the literature. So these are the papers that I have referred for studying this wearable antenna. So from this, I conclude that I require an antenna that will have a geometry like a microstrip antenna. So other than microstrip antennas, few more antennas that can be available are printed dipole, monopole printed loops, slot antennas, planar inverted F antennas. So considering all these challenges, basically large bandwidth, high efficiency, electrical performance, polarization, size, uh, the best suitable one is microstrip antenna. So this is the structure of microstrip antenna, which basically consists of patch. This particular portion is called as patch, whereas this one is the substrate, and again this is the ground plane. So simply a microstrip antenna is made up of patch, substrate, and the ground plane. So such a kind of structure we call it as a microstrip antenna. The one of the important advantage of this can be available in various shapes. For example, right angle, rectangular, elliptical, rhomboid, square, triangular, hexagonal, or circular, or even in pentagonal shape. This can be available. That's why the microstrip antenna suits very well for the wearable applications. Now the material selection. So basically the materials which are available in the market that can be used for manufacturing the wearable antenna are adhesive copper tips like this, or simply you can use a copper foil, or nowadays conducting textile threads or these materials are also available in market. This can be used as a conducting part. Whereas as a substrate, this can be used, that means a foam, or in case of textile, a jeans denim based material can be used either with the black or blue color, or even jute material is also used. Now about the ISM band, for which my title is. So basically the ISM band is nothing but industrial, scientific and medical frequency band, designated for a radio frequency band by ITE These frequency bands were set aside for RF use for purpose other than telecommunication. So low power and short range telecommunication such as Wi-Fi, Bluetooth, Zigbee, wireless telephone, RFID and NFC operate in these bands. Now, my paper is mainly intended for this frequency, that is a frequency of 5.8 gigahertz. This band ranging from 5.725 to 5.875 megahertz, and the center frequency for this is 5.8 gigahertz. So my antenna design is at 5.8 gigahertz. So design equations for antenna at 5.8 gigahertz. I use width and length formula for designing my this antenna. Then input impedance is calculated by using the formula of ZA, that is antenna impedance. Then design parameters, length of the patch, width of the patch, I have calculated based on the formula which are referred in this formula. Based on that, I obtained the geometry like this. This is the length of my patch. This side represent length, this side represent width of the antenna. This is called as a feed line through which antenna will get the inputs, means feeding, and my antenna will resonate. So this is the geometry that I have prepared for the consideration of thickness of foam material at h is equal to 3 mm. So for this 3 mm, my antenna is designed as a part of substrate. So these are the results that I have used for my design while simulating. This is the S11 characteristics. So exactly my antenna is simulating at 5.8 gigahertz. So design calculations and the simulated one are exactly matching. This is what a good achievement for design of this ISM band antenna. Then next is the radiation pattern. This radiation pattern giving the maximum gain of 7.2 dpi, which is a very high gain that I have obtained with the full ground concept. And this is the point where I can say the gain is 7.2 dBi. This is a unidirectional antenna. Maximum power is radiated only in this direction. That's why it is satisfying the unidirectional concept. And this figure represents current distribution. Generally, this orange or red color indicates the best matching of impedance. So whenever I have a reddish or somehow orange color, that represent my antenna is resonating very well at the frequency of 5.8 gigahertz. Then next to that, to analyze this antenna for variable application, as I said, analysis of SAR is very important. So I have analyzed this SAR for the design that I have prepared here. Just like our human tissue model, I have constructed a phantom into the ANSYS software with the three layers, that is mainly skin, fat, and muscle. The skin is 2 mm, fat is 3 mm, and muscle is 4 mm. So with this, I have constructed, and my design, which antenna is pasted on such a phantom model. So under this also, I have checked the value of S11. It is also resonating very well. It is shown with the blue color. It is slightly shifted in comparison with the original one. But whenever we compare this with the on-body performance, it is got obvious because our body is completely lossy and some sort of EM wave absorption is possible. That's why my pattern is shifted. The same thing I have compared in terms of radiation pattern. But for a radiation pattern, my gain value is maintained, though it comes in the presence of human body. And last one, this is the SAR representation over a value of 1 gram and 10 gram tissue. So I obtained the value for simulation results in this manner. Resonating frequency 5.8, S11 18.75 minus VSWR is 1.15, total gain of 7.2 dB. Bandwidth very important for any antenna, that is 470 megahertz. And SAR, ideally it should be less than 2 watt per kg. I obtained it is 1.48. So this is what a well-designed antenna I have simulated with the help of ANSYS HFSO software. This is what the conclusion. I have obtained the bandwidth of 470 megahertz for a gain of 72 dBi, and SAR analysis also carried, which gives the value of 1.489 watt per kg. So these are the references that I use, and thank you.